Good morning and welcome to this lecture. Today we are going to discuss about the spherical coordinate system. In a spherical coordinate system, a point is represented by giving the coordinates r, theta and phi. R represents a distance, theta and phi represent angles. In fact, phi is the same phi that has been discussed or defined with respect to cylindrical coordinate system. That phi is known as the azimuth angle. Theta is known as the elevation angle. For understanding sake, we can call it as a vertical angle. Phi is the horizontal angle. Now let us see what this R indicates. R is the distance from the origin to any point P. In this case, this is R. It is something like imagine any spherical surface and assume that the center of the sphere is the origin. And you take any point on the spherical surface. The distance from the origin to that point is nothing but the radius of the sphere. So here r is the distance from the origin to a particular point P. So r is equal to constant gives me a spherical surface, radius of the sphere. Theta is defined as a vertical angle. For measuring theta, we take z-axis as a reference axis. We say that along z-axis theta is equal to 0. Now as it is, you got a point P somewhere here. Z-axis is not passing through point P. So to make this Z-axis to pass through point P, I need to bend this Z-axis. Now it is passing through point P. This angle is known as theta. So the angle with which the Z-axis has to be bent so that it passes through point P, this angle is known as the theta. Now let us see if theta is equal to constant, what sort of a surface it gives. Theta is the angle made with respect to z-axis. Suppose if this is z-axis, this angle is theta. This angle is also theta. Like that, when I join all these points, it gives me a cylindrical, sorry, a conical surface, a cone. So theta is equal to constant gives me a cone something like this, a conical surface. Phi is equal to constant gives me a plane surface. So here r is equal to constant spherical surface, theta is equal to constant cone, phi is equal to constant a plane surface. In fact, these are the three surfaces which are going to be mutually perpendicular to one another at any point of observation. The limits of theta are going to be 0 to pi radians only. Because when I say that theta is equal to constant, for example, theta as it is 0 to 180 and then 180 to 360. So if you make one full round, we assume that the limits of theta, just like phi, would be 0 to 2 pi radians. But what happens is when I say theta is equal to constant, this is also theta. This is also theta. So the negative angle, suppose if I define this angle as a positive angle, this is the negative angle 0 to minus 180, this is 0 to plus 180. The negative angle will also be included automatically. So effectively, if you vary theta from 0 to pi radians, it is equivalent to varying theta from 0 to 2 pi radians because the negative angle will also be taken into account. Though, of course, it is somewhat difficult to visualize, but these three surfaces, the spherical surface, and then theta is equal to constant, a conical surface, and phi is equal to constant a plane surface. Here you can see that this is phi is equal to constant, this is theta is equal to constant cone, and then r is equal to constant a sphere. These three are going to be mutually perpendicular to one another at any point of observation. For example, at point P, if you observe, these three surfaces are going to be mutually perpendicular to one another. And here once again you can see that the distance from the origin to point B, this is r, this angle is theta, and this is phi. Phi means once again xz plane is taken as a reference plane for measuring phi. We say that is phi is equal to 0. As it is, this xz plane is not passing through point P. To make that plane to pass through point P, I have to rotate this by angle of phi. Now you can see that it is passing through point P. So phi is the angle with which the xz plane has to be rotated so that it passes through point P. The same way we have defined in the case of cylindrical coordinates. So the limits of phi 0 to 2 pi, limits of theta 0 to pi. Next, the unit vectors AR, A theta and A phi. As we have defined, AR is a unit vector having a magnitude of unity whose direction is perpendicular to r is equal to constant surface. What is r is equal to constant surface? Spherical surface. So wherever you want to define AR, at that point, for that part of the spherical surface, drop a perpendicular. This is AR here. A5. A5 is perpendicular to phi is equal to constant plane. And A theta is perpendicular to that conical surface. Let me try to represent here. This is AR. Perpendicular to this is the curved surface. Perpendicular to the curved surface, this is AR. What is A theta? This is the cone. At this point, for that part of the cone surface, drop a perpendicular. This is A theta. Now, with respect to the spherical surface, AR is perpendicular, A theta is tangential. So, the angle between AR and A theta is going to be 90 degrees. Similarly, A phi is going to be perpendicular to this phi is equal to constant plane surface. This is phi is equal to constant plane surface. So, perpendicular to this plane surface A phi. At any point of observation, AR, A theta and A phi are going to be mutually perpendicular to one another. And not only that one, AR cross A theta would be equal to A phi, just like AX cross AY is equal to AZ. And you can write the remaining equations. Now, expressions for DL, DS and DV in the case of a spherical coordinate system. Whatever procedure that we have discussed in rectangular and cylindrical coordinate systems, the same procedure need to be followed. Procedure needs to be followed here. Let us consider a point with coordinates r, theta, phi. This is point P. So point P is considered to be the common point of intersection of r is equal to constant, theta is equal to constant, and phi is equal to constant. So in defining point P, three mutually perpendicular surfaces are involved. Now, if I increase its coordinates by differential values of dr, d theta, d phi, we get another point Q with coordinates r plus dr, theta plus d theta, and phi plus d phi. So in defining Q, another three mutually perpendicular surfaces are involved. In defining both P and Q, altogether six surfaces are involved. So we get a wedge-shaped rectangular box. We get a wedge-shaped rectangular box with sides dr, rd theta, and r sin theta d phi. Like here, one side is dr, one side is rd theta, that is the curved surface. r sine theta d phi, that is also a curved surface. Nevertheless, the dimensions are important. A rectangular box, wedge-shaped rectangular box with sides dr, r d theta and r sine theta d phi. So, what are the expressions for dl, ds, dv? dl is equal to dr ar plus r d theta a theta plus r sine theta d phi a phi. Similarly, for getting area, I have to vary two at a time. Both r and theta are varied. So, r dr d theta a phi, r square sin theta d phi, both theta and phi are varied, keeping r constant. R sin theta d phi dr, both r and phi are varied, keeping theta constant. Because for getting area, we need to vary two coordinates simultaneously. And finally, the volume, all the three have to be varied. Dr into r d theta into r sin theta d phi, that is r square sin theta dr d theta d phi. This is the expression for volume. Now let us see how to make use of these equations. For example, you are defining a spherical surface of radius r. What is constant for the spherical surface? R is constant. Once r is constant, that if you substitute dr is equal to 0, dr is equal to 0, this term would be 0. And then, sorry, second one, dr is equal to 0, then expression for ds, this term would be 0. And then here also dr is present, r dr d theta. So this term also would be 0. So you're left with r square sin theta d phi ar. What is its magnitude? R square sin theta d phi. How do you get the total spherical surface? By keeping r constant, okay, varying theta from 0 to pi and phi from 0 to 2 pi. So we get the total surface area as 4 pi r square. Now similarly the conical surface. How do we obtain the cone keeping theta constant? Once theta is constant, d theta is equal to 0. That you substitute d theta 0. This term won't be there. This term won't be there. So you are left with r dr sin theta d phi. R dr sin theta d phi a theta. Okay. And of course, by integrating this one, you get the total area of the cone. Theta varies from 0 to pi. Okay, so theta is constant. Phi varies from 0 to 2 pi, and r varies from 0 to certain value, let us say capital R. So this is all about the spherical coordinate system.